Oh, yeah, yeah. But okay, all right. Let's. I guess we can try to start the next session. Don't worry about the fact that we're behind. It's not a big deal.
All right.
But yeah. Okay, so take it away.
Okay. Let me share. All right. Does it look all right? Okay. So the plan is to give this second talk, which is going to be very similar to the first talk, but now it's going to be about the Boltzmann equation instead of the Landau equation. Okay. So I'm going to put the same first slide because it says Boltzmann and it also says Landau. But now I'm going to concentrate on the Boltzmann collision operator. So I'm going to study an equation in which the right-hand side is the Boltzmann equation. And I'm not going to worry so much about the space homogeneous case because I think the space homogeneous case is most interesting for the Landau-Coulomb equation. The space homogeneous case would also be open for the Boltzmann equation in the case of very soft potentials. But the Landau-Coulomb is the most extreme case of very soft potential. So it's sort of like the most interesting. I'm going to concentrate more on the space inhomogeneous case of the Boltzmann equation. Okay, and what regularity estimates we can get. So now we have the Boltzmann collision operator. And I'm going to be talking about the non-cutoff case. Why non-cutoff? Because I want to study regularity estimates. And in the cutoff Boltzmann, there is really no regularization effect. We may talk about propagation of the regularity of the initial data, but it would be a very different type of problematic, and that's not what I'm talking about. So I'm going to be talking about the regularization effect that comes in the non-cutoff case. Okay, so the non-cutoff case would be the Boltzmann collision operator with this kind of collision kernel. You may rewrite the collision. This is the way people always write it everywhere. And it may also be interesting to write what it is in terms of the velocities v prime and v star, and this quantity right here is exactly this quantity that I wrote underneath. So it's v minus v prime to this power times v minus v star to whatever power is left, so that you get homogeneity gamma when you add the two powers. Okay. So again, the case of gamma positive is you would call it hard potentials. The case of gamma 0 would be Maxwell molecules. And then for soft potentials, the moderately soft is when gamma is larger than negative 2s. So if gamma plus 2s is positive, our estimates are much more favorable than when gamma plus 2s is negative. When gamma plus 2s is negative, that would be the very soft potential case. And that's the case in which we cannot get L infinity bounds, even in the space homogeneous case. So the analysis for the space inhomogeneous case will only be limited to gamma plus 2s positive, which is in a way more favorable. All right. So this is our Boltzmann collision operator. And you know, when S goes to 1, somehow it converges to the Landau operator of the previous lecture. So in a way, I would like to understand this Boltzmann collision operator as a diffusion plus a lower order term. So let's see how to get that. So let's try to find the diffusion inside the Boltzmann collision operator. Where is the diffusion? So what I'm going to do is let's try to manipulate the Boltzmann collision operator, and let's try to get a different point of view. So I'm going to add and subtract this term, f prime star times f, from that increment inside the Boltzmann collision operator. So I add and subtract f prime star in order to get the common factor of f prime star from the top two terms and get the common factor f from the bottom two terms. So I'm splitting the Boltzmann collision operator Q into this first term and that second term. In the first term, I took common factor f prime, and I'm thinking of f prime minus f times something. And in the second term, I'm taking fv times whatever else I have, right? So I have this this operator here. So this term over here you can do some arithmetic manipulation, and it turns out to be the convolution of f with v to the gamma. This is the so-called cancellation lemma. The first time I saw it was in this paper of the entropy dissipation estimates by, who was it? Alexander, what is Sander, Villani, Wemberg, and Villette, I think. So, this is in the cancellation lemma tells you that this term is f convolution v to the gamma. For the first term, I want to understand this first term as an integral diffusion operator. An integral diffusion operator is f prime minus f times the kernel in terms of v and v prime, right? So the kernel would be exactly f prime star times b integrated along the values of sigma and v star that correspond to the same v prime, right? For every v prime, there is a collection of values of sigma and v star that correspond to that v prime. So you have to integrate along those, put whatever Jacobian you need, and compute this kernel k sub f, which depends on f, right? So it's the diffusion kernel depends on the solution itself. So it's just like in the Landau equation that we had the diffusion coefficients that depending on the solution f. Here we have the diffusion kernel that depends on the solution f, right? So the Boltzmann collision operator is an interdifferential diffusion, which should also be thought about as a quasi-linear diffusion operator that will be in a way of order 2s, right? Plus a lower order term, right? What's my next slide? So this is what the kernel is. The kernel is a fractional Laplacian times this factor. And the factor is the integral of f along the hyperplane through v that is perpendicular to v prime minus v, right? And it's a weighted integral of f. But you see that if all you know about f is that f has finite mass and energy, there is very little you know about this factor, right? So a function with finite second moments, let's say, even a bounded function with finite second moments, may have the integral along a hyperplane to vanish, because maybe the function vanishes on a hyperplane and the mass of f is elsewhere. So we don't have a bound from below for this kernel, at least not for every point v and v prime. We don't have a bound from above either. A function in L1 may easily integrate to plus infinity on any given hyperplane. So even though there is a factor here that looks like the fractional Laplacian, the other factor is not bounded from below and above. So the ellipticity of this kernel is not so easy to understand, right? But still, the term is roughly an interdifferential operator diffusion of order 2s. And see that what we have is an integral diffusion. This is a quasi-linear integral diffusion plus a lower order term. This is sometimes in some papers of I don't know why, since there is a long tradition of writing that the Boltzmann collision operator is the fractional Laplacian plus a lower order term, which is a terrible sentence that is completely wrong, and it gives you the very wrong intuition about what it is. It is an integral diffusion that is quasi-linear, right? The kernel depends on the function itself, and it's not the fractional Laplacian. It's a quasi-linear diffusion operator plus a lower order term. All right. So let's try to understand in which way this kernel should be considered uniformly elliptic. For the Landau equation, we had a diffusion operator that was uniformly elliptic when when we knew bounds for the mass, energy, and entropy of f. Here, we would want to know in which sense this kernel is non-degenerate when we know bounds for the mass, energy, and entropy of the function f. Okay. So that's what we have. This term, exactly this term, converges to the diffusion operator of the Landau equation as s goes to 1, right? So let's see what kind of estimates we can prove on the kernel k sub f when s is somewhere in between 0 and 1. Okay. So let's start from the bounds from below. the kernel of the fractional Laplacian is just the first factor. So we would like to have the second factor bounded from below, but we cannot get the second factor bounded from below everywhere for the reasons I said before. If all we know about the function f is a lower bound on its mass, an upper bound on its energy, and an upper bound on its entropy, then there could be lots of hyperplanes in which the function f vanishes. What we can say is that the function f has to be large somewhere, and it has to be large in some set of positive measure, because the upper bound on the entropy does not allow the measure of f to concentrate, the mass of f to concentrate in set of measure 0. So there will be some set not too far from the origin where f is bounded below, right? So this is this great set over here. If you take any value of v anywhere, there is going to be you're going to have these cones that is where the black cones, which is sort of the projection of those sets where f is bounded below towards v, right? So in those directions, v will see the set where f is large. And if you look at any direction perpendicular to these planes that would hit the set where f is large, then the kernel will be bounded below. So this cone in red is exactly the cone where the kernel is bounded below by a multiple of the kernel of fractional Laplacian. So there are certain directions at any point v, they depend on the point v. So for different points, the directions will be different, but there is going to be a thick cone of directions. So a set of positive measure of directions where you have a bound below on the kernel, right? So that corresponds to the lower bound on the ellipticity, but in the setting of integral diffusions. Okay, so it's a mild form of ellipticity, right? If you the study of integral diffusions was a very fashionable area of research, I would say, for from the beginning of the 21st century. And if you take a paper in integral differential diffusion, integral differential elliptical parabolic equations, at least the first papers in the area were always for kernels that were bounded below and above by a multiple of fractional Laplacian. We are not quite getting that, but we're getting a milder version of ellipticity, which is the kernel is bounded below on a thick cone of directions, not everywhere, but on some directions. Now, it turns out that this is a bound, it is a lower bound that is good enough for many purposes. One of the things that it implies the coercivity of the quadratic form with respect to the kernel. So this is a general statement about interdifferential diffusion operators. If you have a kernel, and there is this condition that is weaker than the cone of non-degeneracy, it says that if you have any ball that contains a point v, then the points v prime in the ball for which this is an assumption. If you have that the points v prime on that ball, on any ball that contains a point v, so that the kernel is bounded below are at least a fixed proportion of the ball b, this is a stronger condition than the cone of non-degeneracy, because if you have a cone, then you take any point that contains the vertex of the cone, and the cone is going to grab some proportion of the ball, right? So it's a weaker condition. If this condition is satisfied, then the quadratic form associated with the kernel is coercive with respect to the HS norm. The right-hand side is the HS norm, but localized to a smaller ball than where I'm doing this quadratic form of the kernel. So the cone of non-degeneracy implies the coercivity for the Boltzmann collision operator. So the coercivity of the Boltzmann collision operator is something that can be proved in a number of ways. And there is several versions of coercivity for the Boltzmann collision operator in the literature. So what I'm saying is that ultimately it's really a property of integral differential diffusions, and you can apply right away this general statement about integral differential diffusions, in particular to the Boltzmann collision operators, because it satisfies this cone of non-degeneracy condition. Okay. Of course, this cone of non-degeneracy is going to be the thickness of the cone of non-degeneracy and the lower bound change for large velocities, right? So when you go to large velocities, the cone is becoming thinner and the lower bound is actually getting better. So the coercivity will be also adapting to, it's going to be changed. This constant, the implied constant of the inequality is also going to be different depending on where, around what velocities you're applying the coercivity, right? So for large velocities, you have slightly different constant or to compare with the HS norm. All right, so that's in terms of the lower bound on the ellipticity. This is like the lower bound on the ellipticity, but in the interdifferential framework. Let's look at the upper bound. For the upper bound, we cannot say that the kernel is bound above by the kernel of the fractional Laplacian, but it's going to be bounded above on average. What do I mean by that? If I integrate on a ball the kernel times v minus v prime squared, then you get the same upper bound as if the kernel was the kernel of the fractional Laplacian, right? The same upper bound as the kernel was the kernel of the fractional Laplacian. This constant gamma, it's also somewhat depending on velocity, and it's roughly the convolution of f with v to the gamma plus 2s. So recall that for the Landau operator, we had the upper bound on the coefficients that was the convolution of f with v to the 2 plus gamma, right? So when gamma was less than -2, things were iffy. Here, we have that the upper bound to be the convolution of f with v to the gamma plus 2s. So when gamma plus 2s is negative, things will be iffy in the sense that the upper bound on the kernel would require some further regularity on f, right? So that's why gamma plus 2s negative would be the very soft potential case. Gamma plus 2s positive puts you in the realm of at least very moderately soft potential. Okay, so this is the upper bound. The upper bound on the kernel is only on this average sense. We don't have a pointwise upper bound for the kernel. And the constant gamma would be controlled with in terms of the mass and energy of f, provided that gamma plus 2s is between 0 and 2. So let's see what can we say about the symmetry. This is the natural symmetry that comes from the construction. K from v to v plus w is the same as k from v to v minus w. And this is the type of symmetry that you would want if you want to evaluate the operator at a fixed point. So let's say that you plug a smooth function into the integral operator. This symmetry allows you to get some cancellation around the origin that makes the integral well-defined in the principal value sense. So this integral is computable whenever f is smooth because of this cancellation, right? And so you should compare that with the non-divergence form, with an elliptic operator in non-divergence form. An elliptic operator in non-divergence form is computable whenever you plug a smooth function because the coefficients are outside of the derivative. If you put the coefficients inside of the derivative and the coefficients are rough, you wouldn't be able to compute point-wise the value of an elliptic operator in divergence form, right? So the non-divergence form operators, elliptic operators in non-divergence form, have the advantage that they are point-wise computable. And that corresponds to this symmetry condition when you look at interdifferential operators. Now, the Boltzmann collision operator satisfies the following cancellation. If you switch v with v prime and you introduce v prime, you get something bounded at, this should be a principal value as well, right? So you get something computable in the principal value sense. You see, it would be convenient, although not true, but it would be convenient to have kernels that you can switch v with v prime and you get the same thing. Because if you have a kernel that k of v prime is the same as k of v prime v, then the associated interdifferential operator will be self-adjoint. And self-adjoint operator, you can always think about, I'm going to multiply times the smoothest function and integrate apart. So the symmetry k of v prime equal to k of v prime v is a desirable symmetry if you want to work with Sobolev spaces, if you want to apply methods analogous to elliptic operators in divergence form. So when you work with interdifferential diffusions, those papers for interdifferential diffusions that try to reproduce theorems of divergence form, like a version of, let's say, of the Cauchy-Nash-Moser, would typically assume that you have kernels that are symmetric in the sense that k of v prime is equal to k of v prime v. We don't have that symmetry. We would be desirable, but we don't have it. But we have this cancellation condition that is a weaker form of that symmetry. And this cancellation condition is enough to make the operator, the interdifferential operator, bounded as an operator from HS to H negative S. So it's, in a way, it's saying that our interdifferential operator is like a divergence form interdifferential operator of order 2s plus some sort of lower order correction, right? So if you compare with the divergence form version of the Landau equation, the divergence form version of the Landau equation has a first order correction, right? And here, my operator is a interdifferential operator plus a zeroth order correction. So if you think about how would this converge to the Landau operator in divergence form, that means that there is a first order correction that will come out of the interdifferential operator as well. The interdifferential operator converges to an operator of order 2 as S goes to 1, but there is always some sort of correction if you think about it as a divergence form operator. So the asymmetry of the kernel tells us that if we think about it as a divergence form operator, there is some subtle correction of lower order, but not quite as clean as if we think about it as an operator in non-divergence form that would correspond to the symmetry that we have by construction. Okay, so by the way, if you unfold the definition of the kernel, so you write down exactly the formula for the kernel, and you write down what it means to have this cancellation. This is exactly the cancellation lemma, the classical is from the year 2000, the well-known cancellation lemma for the Boltzmann collision operator that is just rewritten in terms of the kernel. There is also a higher order cancellation when S is larger than 1/2, but I'm going to ignore it for now. So in the previous lecture, I talked about the Kolmogorov equation, that the Kolmogorov equation had a fundamental solution that was explicit and it was smooth. So it tells us that we can look at, it gives us hope to look at kinetic equations with diffusion and expect to have smooth solutions. Now, if instead of the Laplacian, I put the Laplacian to the S, the fractional Laplacian, it also has a fundamental solution that is smooth, except that we cannot compute it explicitly. If we take Fourier transform in X and V of the fractional Kolmogorov equation, then we can compute the fundamental solution, and it's this expression explicitly in terms of the Fourier transform of the fundamental solution is explicit. And you see, the fundamental solution decays very fast in Fourier variables, right? Because here for any psi and eta, I have a power 2 to the S. Tau goes from 0 to t, so this is not going to be 0 for every value of tau. And this is going to have this is going to grow like negative psi comma tau eta to the 2s, and then it's going to and then it's going to decay it's going to decay somehow like exponential to the negative norm to the 2s. So it decays very fast in Fourier variables, which means that in physical variables, it's infinity, right? So the fundamental solution of the fractional Kolmogorov equation is C infinity. It's a non-negative function that's going to have integral 1 for every positive time, and it's going to be C infinity. It's going to decay polynomially, unlike, for S equal 1, the heat kernel or the Kolmogorov kernel decay very fast in physical variables as well. This one is not going to decay that fast. It's going to decay only polynomially, right? but at least it's going to be integrable and smooth. All right. The exact polynomial decay is not so easy to compute, by the way. It's a little bit subtle. So this tells us that at least, when we look at this simple example, there is a fractional order version of hypoelliptic equation that at least for kinetic equations, it seems to be working well. All right. So what would be the kinetic interdifferential version of the Cauchy theorem? So this is a theorem that we have with Cyril, and it's the interdifferential version of the kinetic de Cauchy that I mentioned in the previous talk. So it's this is sort of like the interdifferential version of the paper of Goltz, Clement, Mouchot, Alexis Vasseur, and Silvestre. So we have the kinetic transport equal some interdifferential diffusion in the velocity variable. So you see, I'm looking at a generic interdifferential diffusion. It doesn't matter here where the diffusion comes from. I'm going to apply it later on to the Boltzmann equation. But first, I want to understand the general principle that would work for any kernel, no matter where it comes from, right? But then I have to see what are the ellipticity assumptions on the kernel that would give me Helder continuity for solutions of a kinetic equation like this. So I want to make the mildest possible assumptions on the kernel K. And interestingly, the mildest possible assumptions are exactly the ones that we can get for the Boltzmann equation, meaning that for the Boltzmann collision kernel, we get the assumptions that we need, at least depending on mass energy and entropy of F, the assumptions that we need to apply this kinetic interdifferential Cauchy theorem, and we don't get much more. So it's quite sharp in that respect. It almost means that it was tailor-made for the Boltzmann equation, but this is really the best we can prove. Right? We cannot go much further than this in terms of generality of the kernel. So the assumptions for the kernel are: the upper bound holds on average. That means that the integral on balls are the upper bound that I mentioned a few slides ago. They satisfy the coercivity inequality with respect to the HS norm, right? This is the coercivity that I mentioned. If you take the quadratic form associated with the kernel, it has to be bounded below, locally, by the HS norm, right? And then it satisfies the cancellation condition, right? So I don't necessarily have to assume the symmetry condition that I told you before for this, because this is the de Cauchy method. It doesn't use non-divergence type techniques. It's purely divergence type techniques. So what we need is a cancellation condition that tells you that the difference between k VV prime and k V prime V is in a way satisfies some cancellation that makes it integrable in the principal value sense. So with those three assumptions, which is a very mild form of ellipticity for k, we get the Helder continuity for solutions of these kinetic equations with integral differential diffusion in V, right? So the Helder continuity depends on the L infinity norm of F and the L infinity norm of the source term. So this is a theorem that if you want to apply to the Boltzmann equation, it's going to tell you that if you have a bounded solution to the Boltzmann equation that satisfies these hydrodynamic bounds on the mass, energy, and entropy density, then it's going to be Helder continuous. So it gives you one step of the improvement of regularity, which is one difficult step in a way. So we also have an interdifferential version of Schauder estimates. So you recall that for parabolic equations, the Schauder estimates where you assume the uniform ellipticity of the coefficients, and in addition, you assume the Helder continuity of the coefficients. What do we have to do now? We have the upper bound on average and the coercivity. That would be like the uniform ellipticity that we assume for the Cauchy theorem. We assume the symmetry condition, this symmetry condition that we have by construction in the Boltzmann case. Notice that we assume the symmetry condition, not the cancellation, because the Schauder estimates or the original Schauder estimates for equations in non-divergent form, right? And this symmetry condition for the kernel is sort of the interdifferential version of having the coefficients outside of the derivative, right? So we want this symmetry for the interdifferential Schauder. And then the last line is in a way the Helder continuity of the coefficients, but in terms of a kernel. What I wrote here is the same as this upper bound on average that I wrote before, but applied not to the kernel, but the difference of the kernel evaluated at two different points, T1x1v1 and T2x2v2. I multiply times w squared, integrate on a ball, and I have the upper bound times the distance between the 2 points to the alpha. So that would be the way to formulate Helder continuity of the coefficients in terms of an interdifferential operator that instead of coefficients, it has a kernel, right? So at every point Tx and V, the kernel is a full function of V prime that has a singularity at V prime equal V. So formulating what it means for that to be Helder continuous, it has to be done in a certain way, which is this way, right? This is sort of like the weakest way that I can think of to formulate the Helder continuity. And then the interdifferential Schauder estimate would allow us to get 2s derivatives. 2s is the order of the interdifferential operator, so we get as many derivatives as the order of the operator. But you have to be careful, because this is the number of derivatives that we get with respect to the velocity variable, right? And I wrote exactly C2s plus alpha because what I'm doing is I'm using the definition of Helder continuity that I told you an hour ago, right? So here we have velocity, we have space, and we have time. They scale, each one scales with a different exponent. And moreover, the equation is not translation invariant, it's Galilean invariant. So when I write C2s plus alpha, I mean the C2s plus alpha, which is I take a function, I subtract a polynomial expansion at a point whose degree is less than C2s plus alpha when I look at this modified degree, where powers of V, powers of X, and powers of T count differently. And then that has to be less than, distance between the points to the alpha, but the distance has to be also the special kinetic distance that takes into account the scaling of the function. In this case, if V has scaling 1, then T is going to have scaling 1 over 2s. And X is going to have scaling 1 divided by 1 plus 2s, right? So the scaling depends on the order of the equation. And X, V, and T have all different scalings. And that has to be accounted. That has to be accounted for when you look at the Helder continuity proof. He asked me, how do you do this proof? Admittedly, the proof is not that different to the proof of the usual Schauder estimates, but the whole, I would say that you're halfway done when you come up with the right notion of Helder continuity and the right notion of kinetic distance. And then, not every proof of the Schauder estimate works. There is one proof by Joachim Serra for Schauder estimates for interdifferential equations, which is extremely flexible, and that's the one that works in this case. Once you modify the distances and the notion of Helder continuity. All right, so again, this is a theorem about generic kinetic equations with generic interdifferential diffusions, no matter where the kernel comes from. So as soon as the kernel satisfies the assumptions, you will have the estimate. A posteriori, we want to apply for the Boltzmann equation, but it is a generic result. So, like for the Landau equation, we need some sort of upper bound if we want to start our regularity analysis. So here we have this result with Cyril and Clément, which says that if you have the non-cutoff Boltzmann equation with gamma plus 2s in the range from 0 to 2, and we have the hydrodynamic bounds, meaning that the mass density is bounded below and above, the energy density is bounded above, and the entropy density is bounded above, then the solution will decay faster than any algebraic rate. When gamma is negative, we need to assume that the initial data already decays. When gamma is positive, it's self-generated. This is would always be true. This is an upper bound in this weighted infinity norms. We don't get, like in the Landau equation. In the Landau equation, we had a Maxwellian upper bound. Here, we don't have a Maxwellian upper bound. We only have faster than any algebraic rate. We cannot even get any explicit exponential bound, right? It would be nice to get something like e to the negative v to some power, but we cannot even get that. But anyway, this is okay for the regularity estimate, that we go faster than any algebraic rate. But I'm just, pointing out the limitations of our analysis. It's also interesting to, to compare this thing, that for gamma negative, we need the initial data to decay. For gamma positive, we need this decay is going to be self-generated. It's somehow comparable to some older results about moment generations. You know that if in the space homogeneous case, it's known that if the initial data has final moments, the moments are propagated for positive time, or if the gamma is positive, then the moments are generated for positive time. But this is a point-wise estimate, so in a way, it's a stronger result because if you know that the solution decays point-wise, of course the moments are going to be bounded, right? So it's a somewhat comparable, but in a way, it's a more favorable result than an upper bound on moments. And it's also for the space inhomogeneous case, in which case you wouldn't be able to do a moment estimate, or you would get something very weak if you look at moment estimate, because it would be integrated in X. So anyway, these are the upper bounds that we have. And so if we put everything together, we can get a conditional regularity for the Boltzmann equation. That is, if you have a solution to the Boltzmann equation, here the collision operator is the non-cutoff Boltzmann operator with gamma plus 2s in between 0 and 2. So some range of hard potentials are fine. We cannot go to the very soft potential range because we cannot get the L infinity bounds, even in the space homogeneous case. But in this range, if we have the hydrodynamic bounds, and in the case of soft potentials, we need the initial data to be bounded to decay faster than algebraic rate. In the case of gamma positive, we don't need anything about the initial data. Then we get that f is C infinity with estimates that all the derivatives that decay rapidly. This is actually an estimate for smooth solutions. So saying that we prove that f is C infinity is not quite correct. But what we prove is all the estimates of all the derivatives of any order, depending on these constants only, right? So in a way, in particular, if you have a short time existence, then that gives you a smooth solution for some period of time. But if these quantities stay bounded, then the function will stay uniformly C infinity for as long as these quantities are bounded. So if let's say if you have if for whatever reason you can get a solution whose mass density, energy density, and entropy density are bounded forever, then the solution will be uniformly C infinity. And that will give you a way to apply, for example, the result of De Villiers and Villani about convergence to equilibrium, right? Because there is this famous result I think it's about 20 years ago by Laurent De Villiers and Cédric Villani, that they proved that the solution of non-cutoff Boltzmann converges to equilibrium, conditional to having the solution uniformly C infinity for all time. So with this theorem, the condition would be reduced to these 4 inequalities only. Okay, so this is the conditional regularity result. Okay, similar to the one for Landau, but now for the Boltzmann operator. And as before, the hydrodynamic bounds are here to ensure that the integral differential diffusion has some form of ellipticity. if I don't have these four inequalities, then our kernel case of f could potentially be very degenerate. And for very degenerate kernels, it's very difficult to get any regularization result. All right. So let me finish everything by saying a few open problems. I mean, there is many more that one can say, but I have only one page, and I wanted to say open problems related to the stuff that I mentioned. So the obvious open problem is, one could be optimistic and say, I want to show that the regularity of the inhomogeneous Boltzmann equation of Landau. That's what we were discussing at the end of the last lecture. But it seems very far-fetched to be able to prove such a thing. I would say that, like we were saying with Jacob, it's more likely that one may be able to prove that there exists an implosion type singularity. That is that in the inhomogeneous Boltzmann or Landau equation, perhaps there is some sort of solution that concentrates at some point. Another open problem is, well, this comes more from the previous talk. If you take very soft potentials and space homogeneous either Boltzmann or Landau equation, the most extreme case would be the Landau-Coulomb equation, get L infinity bounds. That's another problem that if you solve it, it would be extremely well selected. I would say it's another very important open problem. If I have to give a hierarchy of what problem in terms of regularity of kinetic equation will give you the most fame and fortune, unconditional regularity will give you the most, but you're never going to be able to do it. And L infinity bounds for very soft potentials will come second in my hierarchy, and perhaps it's slightly more plausible. And I threw this wild conjecture that is exactly this upper bound, that the maximum of f cannot be stretched by more than this constant from the maximum of the initial data for the space homogeneous problem with very soft potentials, right? I don't really have a counterexample of this inequality for any reasonable collision operator. So I'm not sure where I would stop my conjecture. But if I want to be more modest, I would say for the Landau-Coulomb, I'm fairly positive that is true for any soft potential. It might be true for any reasonable collision operator, but who knows? Kinetic version of Kirchhoff-Safonov theorem, I mentioned it in the previous lecture. I think that's a very interesting open problem. We have the kinetic version of Dichocci-Nash-Moser, but the kinetic version of Kirchhoff-Safonov theorem, we can't quite prove it. And that's an interesting open problem. One that is perhaps not as far-fetched. I told you this result about coercivity estimate for quadratic form associated with kinetic with the interdifferential kernels. It's not a proof. It's not a problem about kinetic equations. So I'm sort of stepping out of the topic of the conference, but it doesn't matter. So I mentioned this coercivity estimate. That is, if this condition is satisfied for the kernel, then the quadratic form associated with the kernel is coercive. Now, this is a problem that I invite you to think about. Try to find conditions on the kernel K that will make this inequality true. So if K is bounded below by a multiple of the kernel of the fractional Laplacian, then it's a trivial inequality, because for any point VV prime, you have that the integrand is bounded below by the integrand on the right-hand side. But it turns out that you don't need every pair VV prime to satisfy the inequality. We have this condition that is that if you have enough points VV prime with this measured condition, then the coercivity estimate holds. Now, we know for a fact that this condition that we have is not sharp, because there are examples of kernels K, which are really singular measures, for which the set of points VV prime that satisfy the inequality has measure 0, because it's a singular measure concentrated on lines. And yet the inequality holds. So we know examples of that. So that means that the condition that we have here is actually far from sharp, because it doesn't even cover all the examples that we know. So in case of the Boltzmann collision operator, you see the Boltzmann collision kernel would give you a coercive operator if the temperature tensor is bounded below. So this condition would be a consequence of the cone of non-degeneracy. The cone of non-degeneracy is a consequence of having a bound below for the mass density, a bound above for the energy density, and a bound above for the entropy density. Now, having a bound above for the entropy density is stronger than assuming that the temperature is bounded below. If you have the temperature bounded below, but the whole temperature matrix is bounded below, then the function f is sort of has to be a little bit spread around. And it's possible to prove using methods that have nothing to do with this, that the Boltzmann collision operator would be coercive with respect to HS norm in that case. And that's the case in which the kernel does not satisfy this condition. So that means that the condition that we have here is not sharp. But anyway, I like this problem because it's very simple, right? Forget about kinetic equation, forget about anything. I just have a quadratic form. What do I need to assume in this kernel to have this inequality? So anyway, that was my most probably the most doable of the 4 open problems that I mentioned. Of course, there is a lot of other minor open problems that one can talk about, but I guess it's time for me to stop. So let's stop here. All right. So I think Jacob left, so that no one is talking now.
No, Hannah left.
You're there.
No, thanks a lot. But about the other questions, so
I think Jacob was running back to the computer, and then he talked when I said that he left.
Okay, Michele, I think, do you want to ask your question?
Yeah, if possible. Thanks for the 2 great talks. I have a question about the blow-up. Like, if you consider quantum particles instead of classical particles, it is observed condensation. So do you expect that a blow-up scenario could be like an explosion of entropy?
You mean in the inhomogeneous case?
No. I'm saying, like, if you consider quantum particles instead of classical particles, we know that there, are observed condensation of those particles.
And that's in the space homogeneous case already.
Yeah, no. Yeah, of course, everything that is known is in space homogeneous case. But I was asking, like, do you expect that a possible blow-up scenario will be an explosion of the entropy? Actually,
I don't expect the blow-up for the space homogeneous case in this case, for these equations. For the space homogeneous case, I don't expect blow-up, and I expect this inequality to be true. So there shouldn't be blow-up. In the space homogeneous case, right? In space inhomogeneous case, I do expect blow-up. But anyway, this is all speculation, right? I'm telling you what I expect. Not what I can prove. Okay, thanks.
Hi, Luis. Thanks again for the nice talk. I had a question concerning the comparison or comment you made about how when S goes to 1, you said that the integral differential diffusion behaves like that slide exactly. So I get that with the sort of De Giorgi and Schauder estimates you wrote that as S goes to 1, it's playing the role of what you had for Landau. But could you comment on this with respect to, say, the grazing collision limits between Boltzmann and Landau?
Well, it actually converges point-wise. If you pick a smooth function f and you just look at this thing, it's going to converge to that for every v. You have to put the right type of normalization. So let's suppose that you have a kernel K that, like I said before, let's suppose that you have capital D, right? Which as I said before, was v prime minus v to the minus b plus 1 plus 2s times v minus v star to the gamma plus d minus 1 minus 2s, right? Plus. So this was my V. But if I really want to get convergence, I have to put some sort of constant here that depends on S.
Okay.
And I want this constant to be something like 1 minus S. If you put this capital B, and now you compute what this operator is, you know, blah, 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 you have kernel K sub F, which is going to be something, right? Then this operator is really for every capital, for every C2 function F and every value of V, this will converge to that. And it's a computation that one has to do. It's related to the fact that if you have any kernel, let's suppose that you have a kernel VV prime, which is V prime minus V to this, times, let's suppose that you have a coefficient here, which is V prime minus V over V minus V. So something that depends on direction, but doesn't change the homogeneity anymore, right? If you look at, and let's suppose that I put here a coefficient 1 minus S. This is a general statement about, let me make a new line. Okay. Let me make a new page. I want to make a new page. New page after Control D. That's good to remember. So the following is a general fact about integral differential operators. Let's suppose that you have the following operator. Let's say L of F is the integral of F prime F, K sub S dV prime, and K sub S is the kernel of the fractional Laplacian, but with something that it depends on direction. Right? So there's going to be a different factor depending on direction. And I had to put this normalization factor 1 minus S. Now, if you take the limit as S goes to 1 of LF of V, this always gives you something like this, where Aij of, let's say, Aij times any matrix Mij would be the integral of A sigma M sigma I sigma J d sigma. This is a general fact about how you recover second order operators from integral differential operators. You always have this limit. So in the case of when you just observe what the Boltzmann collision operator is, it gives you the convergence from Boltzmann to Landau. And the way you prove this, I mean, let me tell you a little bit how you prove this. You look at the integral differential operator and do some sort of Taylor expansion of F. F prime minus F for V prime close to F, you say it's about the second derivative of F applied to V times V prime J plus some terms that vanish when you integrate them, and plus higher order terms. And this is, you do this for V prime minus V small. And then F prime minus F is bounded for V prime minus V, let's say, larger. Then when you split the integral, when V prime minus V is, let's say, large, you apply that F, you use the F prime minus F is bounded, but then this normalization constant makes the integral of the tail go to 0. When you remove any neighborhood of V, the integral of the tail goes to 0 because of the normalization constant. When you look at the integral in a neighborhood of V, then you grab the Taylor expansion. The first term converges to this thing that I put here. This normalization constant is exactly what you're going to get when you integrate V squared times this kernel. So the normalization constant makes the integral of the matrix in any neighborhood of the origin sort of integrate to something of order 1, and that's how you get this thing. And all the other terms are going to be small. So you basically you remove an arbitrarily small neighborhood of the origin from the Taylor expansion. You get the term of the limit, and outside of that, the normalization factor makes the tail of the integral go to 0. So this computation is a general computation for integral differential operator. I mean, it's something that in integral differential operators, everyone knows it forever. And in particular you can get the pointwise convergence from the Boltzmann operator to the Landau operator.
Okay, thank you for clearing up the connection there.
All right.
Maybe it's a small question. Oh, sorry, Alex, go ahead. My question is less important.
Oh, thank you very much. Thank you for the talk. I'm quite new to the field. I wonder if I could ask just a couple of top level.
We all are.
Well, I don't quite believe it for yourself, but okay.
Except Bardos. I think Bardos has been in the field for quite a while.
I wanted to ask a question, first of all, about motivation. You know, a lot of the work here seems to be directed at proving regularity or counterexample. Now, I understand that for Navier-Stokes, it's a Millennium Prize problem, so it's very high profile and very important. Is the motivation to consider regularity here kind of, you know, inherited from that this is a higher order description of fluids?
Well, there is no money reward here, but the problem is quite comparable, right? You want to show you're given an equation. You want to know if the equation has a solution, right? First question. If the equation doesn't have a solution, what are we looking at? So in order to show that it has a solution, first thing you look at is whether it has a smooth solution, because classical solution, right? Perhaps you can prove that there exists some sort of renormalized solution with defect measure, right? That's a weak solution of Villani. But that sort of solution is a very weak notion of solution, and there is a priori you don't know if they're unique. You don't know if there is a singularity that emerges from the flow. So it's a basic understanding question of any PDE, whether the solution will remain smooth or there will be singularities that emerge from the flow. So it's something that you study for any equation. In parabolic equations, in general, you want to study the regularization effect, because that's something that the heat equation does, right? You get any rough initial data, the solution becomes smoother as time goes by. So that's sort of the qualitative behavior of parabolic equations, and that's sort of the qualitative behavior that we are trying to observe in the Boltzmann and the Landau equation as well, at least in the non-cutoff Boltzmann. So yeah, it's one of the basic questions when you study evolution equations, is whether a singularity can emerge from the flow or not. Because if a singularity emerges from the flow naturally, then you want to understand what kind of type of singularities you can have, and then you want to, you know, the equation is you have to understand what way the equation folds and what happens after the singularity. You know, it's a basic question when you study evolution equations, whether a singularity emerges or not. The reason why it's important is the same reason as why it's important for Navier-Stokes, except that we don't have a bounty if we prove it, right? But it's a question that mathematicians ask about basically any evolution PDE, right?
Well, the last one you made it sound like we ask it out of habit, but that's a fair enough reason, I guess.
Well, I mean, it's what you need if you want to understand the equation. Kinetic equations are complicated equations in the sense that I don't know how much you're able to solve them, right? If you want to prove anything about an equation, it's often useful to have a priori estimates. Let's say you want to prove that they converge to equilibrium as time goes to infinity. So the results that we have are conditional to having the solution uniformly smooth. So they depend on the smoothness. You want to prove that you can derive hydrodynamic equations from the kinetic equations. Well, I mean, that doesn't require as much regularity, right? So maybe there are ways around. But you know, maybe there is something that can be used eventually. So having a priori estimates is something that is central to analysis of PDC in general. If you want to run, let's say, a numerical method to solve a kinetic equation, the rate of convergence of numerical methods always depends on the smoothness of the solution, right? So the smoother you can prove the solution is, then the better chances you have to having a good numerical method, right? And in general, you want to understand what's going on. And if you don't know if the solution is becoming singular or not, you can arguably say that your understanding of what's going on is not as great, right?
Well, I think you answered that very comprehensively and convincingly, so thank you. I guess I wanted to ask just a follow-up as well about, I suppose, the space of collision operators that we tried to do this for. Obviously, you focused on the Landau and the Boltzmann ones, but there's also, you know, parameters we can choose within there.
Yes.
And I suppose that from the pure science side, I'm very pulled towards, yes, we want to understand this for everything, but then for applied research, obviously there's particular ones which come up a lot for certain applications.
Right.
What do you think is the right way of distributing our attention across the most general ways of approaching this, and then these specific?
The Landau collision operator is the one that comes up when you study particles that repel each other by Coulombian potential. So it would be like, would come out in the study of plasmas, right? When you study the plasma in the inhomogeneous case, you know, perhaps it makes more sense to study more some sort of Vlasov equation. I don't know. But the way I set up the equation, I don't have a mean field, but I only have local interaction of particles. The non-cutoff Boltzmann is something that will come up with microscopic models where the particles repel each other by some power law potential, but then the gamma and S are related. So when S is 1, we should be looking at the Coulombian case. When S is between 0 and 1, then we should be looking at certain gamma that is related to S. I decoupled the values of gamma and S, right? Thus, if you believe that the equation comes from these microscopic models where particles repel each other by some power law potentials, what the reality is, I have no idea. And I don't know if anyone does. You know, you can come up with particle models that converge to something. I don't know really what the physics could be very complicated. There could be different type of particles mixed together. The particles may be behaving differently at different scales. I have no idea what the real physics is. I'm sure there is lots of people in the audience that understand it better than me. But I don't know if they understand it so well either, right? At the end, who knows what the physics does, what particles can do or cannot do. If there are many different, there are probably different situations depending on what kind of particles we're talking about. And so because of the motivation from particle models, the Landau-Coulomb operator is the most easily motivated from physical grounds, right? And the non-cutoff Boltzmann can be motivated from these power law potentials when gamma and S are related by certain formula. But the power law potentials are not Coulombic. So again, it's not entirely clear if there is any particular type of gas that gives you that sort of operator. Who knows, right? If you have the particles like billiard balls, you get cutoff Boltzmann. But I don't know if the particles are really billiard balls. I always like to think about particles like being sponges that bounce against each other, because then you have no idea what the Boltzmann collision operator is, right? And I believe it's more like the non-cutoff than like a cutoff, because like a sponge. What is a sponge, right? A sponge would if you look at the center of the sponge, it would repel each other by some sort of power law, maybe when they're sufficiently close. But if they are far from each other, they don't even see each other, right? So I think you get some sort of non-cutoff Boltzmann, but I don't know what happens with the spin of the sponge. That's what I don't quite understand. So anyway, I'm very bad at physics, so I'm sure I'm saying lots of wrong things right now. So I better shut up.
No, Luis, don't shut up. I have a last question for you.
Yeah.
Okay, so it's not about physics, it's about your math intuition, because I have zero intuition for that, and I know you worked on that a lot. Krylov-Safonov, in the kinetic case,
Yes.
would you put your money on it to be true or not? I mean, I have zero idea. I mean, of course, it's clear.
I will put the
to me.
money. I will put the money on Krylov-Safonov to be true. In fact,
Ah.
I would say that intuitively, Krylov-Safonov comes up more natural than the Churchy-Nash-Moser. Because if you think about, I told you, why is the Kolmogorov equation, why does it have a smooth solution? No, this is not right. Why, what's the way to get the next page? Next page, Control D. I forgot about that. So why would the Kolmogorov kernel have a smooth? Why would the Kolmogorov equation have a smooth kernel? I didn't give you any intuition why that happens, because I don't really have a good intuition, admittedly, right? You can compute it, or you can take the Fourier transform, which is equally devoid of intuition, and get that the solution is smooth, right? And if you try to understand what's going on, perhaps you get some intuition if you think about it probabilistically. You know that the heat equation is related to Brownian motion. So you can think about some diffusion where I'm going to look at the diffusion with respect to V to be diffusion with respect to Brownian motion. I'm going to look at diffusion with respect to X to be V times diffusion with respect to T. So if you look at this stochastic process, then the generator is exactly V grad X minus Laplacian with respect to V. So you get the Kolmogorov equation is related to this stochastic process. If you think about dV to be Aij, dBij, dx equal V dt, you get a diffusion operator. Well, not quite. I have to put a sigma here. And then you get a diffusion operator where Aij as a matrix is sigma squared over 2. So when you think about the proof of Krylov-Safonov, it was originally thought in terms of probabilistic terms. The original proof by Krylov-Safonov was about if you take a diffusion process, you start at the point, and you have a set with positive measure, then your diffusion is going to hit this set before leaving the domain with certain probability. So it's all about the probability of hitting sets of positive measure. And the idea is diffusion goes everywhere. The set of positive measures will be hit with positive probability because the diffusion is going to be spread around all the space. Now, if you look at this diffusion, at this stochastic process now, which is plain diffusion in V, but this is the way the X variable evolves, then because V goes everywhere, then the X variable can also go everywhere. So this stochastic process will spread around all space. Now, this is an intuition that leads Krylov-Safonov proof. And it's also present here. This thing will see everything. So I cannot prove that a set of positive measures will be hit by a process like this. But one can prove, for example, that if you start at any xv, and you take a ball around xv in R2D, and you take a ball here, then you will hit this ball with positive probability. A ball, you know, is much more specific than a set of positive measure, right? If I could go from ball to set of positive measure, then you would prove the kinetic Krylov-Safonov. So this probabilistic intuition suggests that the kinetic Krylov-Safonov should be true. Whereas for the kinetic, the Churchy-Nash-Moser, I don't really have a good intuition why it's true. It's just that we know how to do every step of the proof. It's funny, right? Because you would believe that you should be able to do the one that you have intuition, and you should not be able to do the one you don't have intuition. And here is the opposite, right? For the Churchy-Nash-Moser, I don't really have a good intuition why it works. but it just does. And for Kirillov-Safonov, there is some intuition that suggests it should be true, but we don't know how to do it.
And do you think it would have applications to something else? Because you remark that for lambda Coulomb you can use either divergence or non-divergence theory.
Yeah. I don't have an answer for that. Like I said, you can use either one. So for the purpose of understanding Landau operator, Landau equation, either one works just the same. But if let's suppose that in a century from now, someone is writing a book and knows how to do the Kirillov-Safonov version. If let's say all other things being equal, I would rather prove Kirillov-Safonov and apply it to Landau than the Churchin-Ashmoser, because the Landau operator is much cleaner in non-divergence form, right? So I don't want to deal with first order correction. I would rather deal with a 0th order correction. So it doesn't have any application, but it would make the proof nicer, or the analysis nicer.
Okay, so I think maybe we've exhausted the questions for now. So Luis, thanks a lot. That was a really interesting course and quite illuminating. We're a bit behind schedule, so should we
It
just
wasn't
start?
my fault. It was not my fault. My lectures were
It's not your fault.
less
It's not
than
your
1
fault at
hour.
all, in fact.
Yeah.